Imagine a cold, damp night in Cambridge, 1967. A young graduate student, Jocelyn Bell Burnell, sits in the lab, surrounded by miles of paper charts covered in strange zigzags. This is data from a new radio telescope. The clock ticks monotonously, her coffee long gone cold. And then, amidst the universe's endless white noise, she finds it. A small, yet impossibly regular pulsation. Scruff, as she nicknamed it. Short, sharp bursts, repeating with mathematical precision like a metronome. Every 133 seconds. What was it? Alien beacons? Mysterious little green men? It turned out to be something even stranger. A pulsar, a neutron star spinning at a mind-boggling speed. An object so dense that a teaspoon of its matter would weigh 1 billion tons. 1 billion? Can you imagine that? But listen, that's just a prelude to something truly astounding. Pulsars are cosmic clocks. But what if, deep in space, there are clocks that don't just tick off time, but process it? That don't just emit signals, but store information? What if, at the very foundation of our universe, lies a gigantic, ancient processor? Yes, I'm talking about black holes. Those bottomless abysses that seem to swallow everything without a trace. Forget about calculations. They, as we're told, give nothing back. Just absolute devourers. But do you know what's craziest? Theoretical physicists are increasingly whispering. Black holes might be much more than just cosmic trash cans. Imagine a black hole. Not just a gravitational vacuum cleaner, but a kind of cosmic supercomputer, operating for billions of years. What nonsense, a skeptic would say. How can a lump of collapsed matter be a computer? It has no buttons, no monitor, not even electricity. And I get it. It sounds like the plot of the wildest sci-fi novel. Nothing short of a fairy tale. But let's think about it. What is a computer? A device that stores and processes information? And black holes? They store information incredibly efficiently and can even reprocess it. We're not talking about silicon chips, but about the physics of information, the laws of entropy, and quantum quirks that make scientists scratch their heads. Imagine we have a cosmic processor, the size of a galaxy, or even smaller, the size of our world. And it quietly ticks away, processing for eternity. Do you see what I'm getting at? This isn't just a metaphor. It's an invitation to delve into the deepest understanding of the universe, and to look at black holes not as an end to everything, but as a possible beginning. The beginning of the most massive computations. A cosmic supercomputer, operating for billions of years. Ready? Then let's dive in. London, 1783. A damp November evening. In the dusty, old parchment-scented library of the Royal Society, a clergyman named John Michel slowly writes a letter. He wasn't just a clergyman, but a true polymath. A geologist, astronomer, philosopher. And in this letter to his friend Henry Cavendish, Michel describes something that, at the time, seemed like pure madness. Imagine the dim candlelight dancing on his face, the quill scratching as he writes lines about stars so massive that even light cannot escape their gravitational embrace. Yes, a full century before Albert Einstein was even born, Michel was already pondering dark stars. How about that? Back then, it sounded like science fiction, some crazy fabrication. What nonsense! A skeptic of that era would probably have yelled, tapping their temple. Light always escapes. It's an axiom, they'd say. But you know, over 2 centuries later, these dark stars got an official name. And it's far more dramatic. Black holes. And this, my friends, is where it gets really interesting. Because these cosmic monsters, these bottomless voids in space-time, they aren't just devourers of all things. Oh no, that's too simple too, mundane. Imagine a giant incinerator that doesn't just burn waste, but manages to produce, say, new energy, or even thoughts from it. Sounds wild, right? But black holes, they're much wilder. They are the final destination for anything that crosses their boundary, the so-called event horizon. Once you're in, farewell world, farewell, laws of physics as we know them. It's like falling into a whirlpool from which there's no turning back. And even if you're a record-breaking diver and your bathyscarf is made of adamantium, you still won't resurface. Not a single particle, not a single photon returns. So, this irreversibility is one of their most mysterious features. What happens to the information that falls into a black hole? To every book, every bit of data, every thought recorded somewhere in the universe and devoured by this monster. Most physicists, frowning, will tell you information is lost, it vanishes, as if it never existed. This is the so-called black hole information paradox, and it has driven the brightest minds on the planet mad for decades. Imagine you record an entire library onto a flash drive, then throw the flash drive into a shredder that not only destroys the medium, but erases the very existence of the data. A complete wipe. But wait, what if it's not like that at all? What if a black hole isn't just a cosmic shredder, but something far more complex? What if it's not just a vacuum cleaner that sucks things in and forgets, but something else? Something that processes this information for billions of years. This thought, I confess, is a little unsettling. It's like being offered a look at a food processor that, it turns out, can compose symphonies. London, 1832. Imagine a foggy, damp morning, the smell of coal and wet stone, the clatter of carriage wheels on cobblestone streets. In one of the respectable houses, at a table covered with blueprints and diagrams, sits an engrossed man, Charles Babbage, inventor, mathematician, a true visionary. Next to him, listening intently to every word, sits young Lady Ada Lovelace, daughter of Lord Byron himself, a mathematical genius who even then saw something more in his analytical engine than just a calculator. She saw the potential for creativity, for music, for processing information that didn't even exist yet. They spoke of numbers, of logic, of the steps a machine would need to take to solve the most complex problem. Essentially, they were discussing how to package information and make it work. They were building the first architectures for what we call a computer today. Incredible, right? In the age of steam and crinolines, the foundations of the world in which you are now reading this text were already being laid. But do you know what's most amazing? A century and a half later, in our own era, physicists would begin to understand that not just man-made machines, but nature itself, its grandest objects, can be incredible information processors. And this is where they enter the stage: black holes. Remember how we talked about them as cosmic monsters, devouring everything in their path? Well, these vacuum cleaners presented scientists with one of the biggest and most perplexing puzzles of modern physics. It's called the information loss paradox. Imagine for a second that you are the most meticulous librarian in the universe. You record every little detail, every bit of data, every particle, its energy, spin, position. All of it is information. All of our physics is built on the unwavering foundation that information cannot disappear without a trace. It can transform, change, but never vanish. Now imagine your most valuable volume, containing an entire galaxy of data, falling into a black hole. And then what? According to classical understanding, a black hole swallows this volume and leaves behind only three characteristics: mass, charge, and angular momentum. That's it. It's like burning down an entire library and then saying all that's left is one brick. Hold on a minute, physicists clamored. What kind of trickery is this? Where did all the information about the book go? Its pages, letters, the history it contained? Did it just vanish? This was a real nightmare for quantum mechanics, which stubbornly insists information does not disappear. Never. Under any circumstances. It's as if you deleted a file from your computer, but not a single byte was left on the disk. Not even fragments. Just nothing. Stephen Hawking, a genius who did so much to understand black holes, at one point himself adhered to the idea that information disappears. He spoke of Hawking radiation, the slow evaporation of black holes. But according to his early calculations, this radiation was completely random, carrying no memory of the absorbed matter. It's like listening to the static of an old radio, trying to figure out what song was playing on it 10 years ago. Useless. So, a black hole is a kind of universal trash can that not only devours, but also erases data? So what? A skeptic might ask. Some information got lost. The universe is big. It'll manage somehow. But this isn't just some information. This is about the fundamental laws of the universe. If information can disappear, it means our understanding of the universe is riddled with a huge hole. It's like finding out that the strongest bridge in the world is built on a single rotten pillar. The entire structure risks collapsing. It was this paradox, this mystery, that literally made scientists worldwide rack their brains for decades. How can something swallow an entire star and then evaporate, leaving no trace that the star ever existed? The answer that slowly began to emerge was as bold as it was elegant. What if black holes don't just destroy information? What if they process it? What if they're not just cosmic abysses, but something far more complex? What if they are the most incredible computers in the universe for billions of years, working non-stop on problems we can only guess at? Stephen Hawking, our genius in a wheelchair, initially claimed just that. Information is lost. Physicists were like, "What nonsense! Are you breaking the very foundation of our universe?" Thus began the great black hole information paradox, which tore scientists apart for decades. And then a crazy but brilliant idea emerged. What if black holes don't destroy information? What if, like the most sophisticated hard drives, they record it? Imagine every atom, every photon, every grain of sand that crosses the event horizon leaves its digital trace. It's as if you throw a stone into a pond, and instead of it simply disappearing, the information about its shape, mass, speed, energy, everything, is encoded in the ripples on the surface. Or, if you prefer, in invisible bits on the surface of the pond itself. Yes, exactly. Not just a hole, but a colossal, ancient, unimaginably capacious data recorder. Billions of years of accumulation, storage, and this is where it gets interesting, perhaps even processing of everything that has ever fallen into them. Do you understand? This is no longer just a graveyard for stars. This is the beginning of something much greater. This is the beginning of the idea of a cosmic supercomputer. November 1948, the somber walls of Bell Labs, New Jersey. The sky outside is overcast with gray clouds, and inside, in the smoke-filled offices, a tense silence reigns. A young engineer, Claude Shannon, hunches over his calculations, lost in deep thought. He wasn't inventing a rocket or an atomic bomb. He was inventing something that would forever change our understanding of the universe, from communications to the very foundations of existence. He was defining information. Imagine this moment. Not a grand explosion, not the brilliance of a supernova, but a quiet, almost imperceptible click of thought that gave birth to the bit. Yes, that very bit from which everything you are currently reading, watching, and hearing is composed, from cat memes to the most complex scientific data. Just a 0 or a 1, yes or no, on or off. It sounds so simple, almost primitive, but in this simplicity lies the entire complexity of the universe. And you're probably scratching your head in bewilderment, thinking, listen, narrator, what do black holes and their cosmic supercomputers have to do with any of this? We're talking about space, not telecommunications. And I'll tell you, Shannon, without even realizing it, laid the foundation for one of the most insane, incredible, and all-encompassing ideas in modern astrophysics. Because information, my friend, turned out to be not just a key, but an entire labyrinth to unraveling these cosmic giants, capable of turning our understanding of them completely upside down. Ready? Then buckle up. We're starting our dive into a world where black holes are not just devourers of all things, but something far, far more complex and fascinating. For a long time, physicists and all of us considered black holes to be cosmic vacuum cleaners that simply suck in everything in their path. What fell in was gone, irreversibly. No traces, no memory, just an endless black abyss where everything vanished. Matter, energy, and most importantly, information. How else could it be? Well, your old refrigerator fell into it, and that's it. It's gone. And all the information about its brand, color, year of manufacture, the smell of rotten pickles, all of it seemed, should have dissolved into the singularity, into a point of infinite density where the laws of physics as we know them cease to work. That was the established picture, simple and clear, and completely wrong, or at least incomplete. But then, in the 1970s, Jacob Bekenstein stepped onto the scene. Young and audacious, he dared to challenge this dogma, supported by the greatest minds of his time, including Stephen Hawking himself. Imagine the scene. A young scientist declares that black holes don't destroy information. Can you picture the reaction of the scientific community? What? Information doesn't vanish in a black hole? Are you out of your mind, young man? You know that contradicts all our understanding of information conservation in physics. Seasoned professors probably yelled in his face, waving their hands and spitting. Many perceived his ideas as heresy, as outright madness that undermined the foundations of everything they held sacred. Bekenstein, however, was unfazed. He declared that black holes have entropy. Yes, that very entropy, which is a measure of chaos, or if you like, a measure of information in a system. The more entropy, the more ways to arrange particles, the more bits of information. That was already quite bold. But then he made a statement that made physicists' hair stand on end. He calculated that this entropy depends not on the black hole's volume, but on its surface area. Wait a minute. Stop. Let that sink in. Not on its volume, on its surface. It's as if all the information about your three-dimensional apartment wasn't stored inside, in every corner, but was exclusively drawn on its walls, ceiling, and floor. As if your ultra-modern terabyte hard drive stores data not within itself, in its magnetic platters, but around the perimeter of its casing, on a thin outer shell. Physicists grabbed their heads. How is this possible? We're used to volume meaning capacity, but here, It turns out that the entire complexity of the contents can be described by something flat, two-dimensional. And this is where we come to the main turning point, to an idea that changes everything. Remember holograms, those shimmering images that appear three-dimensional, even though they're actually a flat piece of plastic on which the volume is encoded. Imagine that our universe is a gigantic, incredibly complex hologram. And everything that happens in three spatial dimensions is actually recorded on a two-dimensional surface somewhere at its edge, or, in the case of black holes, on their boundary. This is the holographic principle. Sounds like science fiction, right? Like a script for a blockbuster about the Matrix. But for black holes, this isn't just fantasy. It's very real, albeit mind-boggling, physics. Bekenstein, and later Stephen Hawking, who was initially skeptical of Bekenstein's ideas, but then made immense contributions to the theory himself, showed that information about everything that falls into a black hole doesn't disappear. It is recorded, or if you will, imprinted on its event horizon, that invisible boundary from which there is no return. The event horizon becomes this gigantic, cosmic bulletin board on which the entire history of the black hole is etched, literally every event, every particle, every photon that has ever fallen into it. It's not just a boundary, it's a screen, an interface, a kind of display of all its internal complexity. And each of these bits of information, each pixel on this cosmic screen, it has a minimum size. It cannot be smaller than a certain limit. This limit is called the Planck area, an incredibly, mind-bogglingly small value, approximately 10 to the minus 71st power of a square meter. It's as if you were trying to see an atom through an electron microscope, only billions of times smaller. Imagine that all the information about every atom that has ever fallen into this abyss is encoded on its surface in these tiny, almost unimaginable dots, like on a flash drive with infinite memory. This memory isn't just an abstract concept. It's real. It possesses physical properties. If you could somehow incredibly examine the event horizon of a black hole from a close enough distance, you wouldn't just see a smooth black sphere, but something like a grainy, swirling screen, where each speck is a bit of information. This isn't a static recording. It's a dynamic process where new bits are constantly added, and old ones are perhaps overwritten or give way to new ones. So, when we talk about black holes as supercomputers, we don't mean silicon chips or cooling fans, and certainly not the processors we're familiar with. We're talking about them being colossal, fundamental repositories of information. Immense repositories. They absorb information from the universe, record it on their surface, and store it for billions of years, outliving entire galaxies. It's not just a disk array. It's an entire cosmic archive that is also constantly being updated. Every black hole, from the smallest to the supermassive giants in galactic centers, is a living, breathing, well, almost information node. Of course, this isn't the computer in your pocket that can run TikTok, or a supercomputer calculating weather models. It's something far more primal and fundamental. It's more like a universal processor that continuously collects and encodes data about matter and energy in the universe, using the very fabric of space-time, the laws of quantum mechanics, and gravity to do so. It doesn't compute in the usual sense of the word, but it processes and stores information with inconceivable efficiency on scales that are difficult to even imagine. It is the most durable and highest capacity information carrier in our known universe. Physicists are still racking their brains trying to understand exactly how this information is read or processed, and how it interacts with the internal processes of a black hole. But the very fact of its existence, its storage on the surface rather than inside, opens the door to an entirely new world of understanding about black holes. A world where they are not just monstrous devourers, eternally hungry cosmic beasts, but rather cosmic libraries, guardians of the entire history of the universe. Or, as we've said, supercomputers that operate in the background for billions of years, compiling their immense, comprehensive database about our world and, perhaps, about worlds that existed long before us. They are not only the end of a journey, but also the beginning of a new understanding of data, its storage, and, who knows, its processing. Remember how, at the end of the 19th century, in a chilly but scientifically bustling Vienna, there lived a genius named Ludwig Boltzmann, a man with a thick mustache and an equally thick beard, who didn't just observe the world, but tried to understand its internal, chaotic pulse. In 1877, he published his works that forever changed our understanding of order and disorder by introducing the concept of entropy. Imagine, he's sitting in his office, buried in papers, smelling of coffee and ink, and in his head, ideas swirl about how any substance isn't just mass, but an enormous, unimaginable collection of tiny particles, each of which can be in millions of different states. His colleagues, of course, grumbled, "What nonsense, Boltzmann! Your atoms are just a convenient fiction." But he knew. He felt that behind the seeming chaos lay the deepest mathematics, and entropy was a measure of that chaos, but also a measure of the information that could be encoded in a system. And now, let's fast forward a century to black holes. Do you know what's most astonishing? Even these cosmic devourers, seemingly perfect in their simplicity, have entropy. Stephen Hawking and Jacob Bekenstein proved in the 1970s that black holes don't just swallow everything indiscriminately. They increase the total entropy of the universe. It's as if you threw 1,000 books into one enormous bottomless pit, and that pit somehow miraculously remembered every page, every symbol. Of course, the skeptic within you is probably already indignant. How did it remember? A black hole doesn't let anything out. Information should be lost forever. And you'd be right, if not for one of the most dizzying ideas in modern physics, the holographic principle. Imagine that all the information about a three-dimensional object, for example, about you or a galaxy, can be completely recorded on a two-dimensional surface, like a hologram, as if the entire library you threw into the hole didn't actually sink to its center, but neatly arranged itself on its surface, on the event horizon. This isn't just some abstract image, it's a serious mathematical concept. A black hole's event horizon isn't just a boundary, it's like a gigantic quantum display on which everything that has ever fallen into it is recorded. Every atom, every particle, every wave of light, all of this leaves its trace, like a pixel on a screen, but in an incredibly dense quantum form. This is where the most exciting part of our story about cosmic supercomputers begins. If all the information about a black hole's contents is stored on its surface, not in its volume, then this surface isn't just a passive storage device. It lives, it fluctuates, changes, reacts to every falling photon, to every neutrino wave passing by. Imagine this event horizon as a gigantic, constantly updating neural network composed of the tiniest quantum bits of information. It's not just a data storage disk. It's an actively working processor that continuously recalculates, reprocesses, recodes the entire absorbed universe. Billions, trillions of years. That's how much time a black hole has to work on this colossal dataset. It's like a cosmic sponge that doesn't just absorb water, but somehow analyzes it, sorts it, and perhaps even creates something new from it on its surface. Do you understand? It's not just a void that attracts everything around it. It's a complex mechanism that perhaps never sleeps, processing all the information that destiny has provided it. Maybe it doesn't just store data, but also finds patterns within it, or perhaps even models alternative realities, all on one seemingly ephemeral boundary. Mind-boggling, right? Imagine, listener, a cold, foggy dawn in the English county of Buckinghamshire at Bletchley Park. 1942. War rages and the fates of millions hang in the balance. Inside unassuming brick buildings, behind curtained windows, work is frantic. Not soldiers with rifles, no. Here are mathematicians, linguists, chess masters, geniuses whose weapons are their brains, and the first, bulky, humming electromechanical machines known as bombs. Their mission? To crack the elusive code of the Enigma, the Nazi cipher machine that seemed to speak the language of the gods themselves. You see these people, sitting in smoke-filled rooms, poring over endless punched card tapes, trying to extract even a shred of meaning from the chaos of symbols. It was a desperate battle for information, a battle to understand a hidden message. And with their titanic efforts, their pure genius, they created the first truly complex computational systems that crunched gigabytes of data in search of invisible patterns. Now let's fast forward 13 billion years into the cosmic darkness where the first black holes were born. No light bulbs, no paper tapes, no hum of machines. Only gravity, time, and something far more fundamental than the gears of a bomb. You're thinking, how can a black hole be a computer? It just swallows everything. And I agree, it's not intuitive. But listen, remember how we talked about information? Well, one of the deepest discoveries in physics in recent decades is that information, it seems, never disappears without a trace. Never. Even if it falls into a black hole. Imagine that the event horizon isn't just a one-way boundary, like a bank vault door that only opens inward. No, it's much more interesting. It's, if you will, a gigantic ancient cosmic hard drive. Or better yet, it's a two-dimensional screen on which, in the finest detail, in quantum pixels, all information about every atom that has ever crossed that boundary is recorded. This is called the holographic principle, and it literally blows your mind. Physicists at first are like, what nonsense? How can this be? And then they start digging, and it turns out that the mathematics confirms it. All three-dimensional information about the interior of a black hole can be encoded on its two-dimensional surface. Like a hologram, where a volumetric image is stored on a flat film. So what, you might say? It's recorded. So what? How does that make it a computer? It's just storage. Excellent question. And here we come to the most interesting part. Firstly, it's a storage device with unimaginable capacity. Think about it. All the information about a star, about galaxies of gas and dust, about millions of years of history compressed onto a surface. Secondly, the information isn't just lying there. It interacts at the quantum level. Photons, elementary particles that make up light and everything around us, they don't just fall in. They leave their mark, they change the state of the pixels on the event horizon. These pixels are not just points. They are quantum bits of information, qubits. And these qubits, listen closely, can be linked to each other. Entangled. One qubit changes state, and others change with it. This isn't straightforward computation, like on your laptop. It's not 2 + 2. It's more like a gigantic, constantly swirling, self-organizing network. A quantum network for billions of years, in which billions, trillions, quadrillions of interactions occur every second. Every atom falling into a black hole, every quantum of energy, every particle of light, that's data input. And the event horizon, this cosmic boundary, constantly recalculates, reprocesses, rewrites this data. Imagine you throw an entire library into this hole. All the books, pages, words, they don't just disappear. They break down into their fundamental informational units and are recorded on the surface. And then, these units begin to communicate with each other, forming an incredibly complex dynamic computational system. A system that processes everything it sees and absorbs in its corner of the universe. It doesn't just store, but interweaves, rearranges, creates new connections. So, my friends, if Max Planck's idea seemed like madness in his time, then what we're about to discuss might strike you as true cosmic surrealism. And once again, we'll be talking about information. Remember how we talked about black holes not losing the information they absorb? So what, a skeptic might say, scratching their head. So they don't lose it. What then? That information just sits there, quietly, gathering dust on the shelves of some cosmic archive. No one reads it, no one processes it, just a warehouse. And that's where it gets truly interesting. What if this warehouse isn't just a warehouse? What if it's a gigantic, operating for billions of years, supercomputer? Imagine, not just an information carrier, but an active processor. Sounds like science fiction? Keep listening. First, let's clarify. What is information for a black hole? It's not your old photos on a flash drive. It's every atom, every photon, every quantum of a field that has ever crossed the event horizon, with its exact position, speed, spin, charge, a complete dataset about the incoming client, if you will. And a black hole, it doesn't just swallow all of this. It encodes this information on its surface, on the event horizon, like on the surface of a gigantic hard drive that is constantly being rewritten and updated. On this disk, an entire universe of data. And here we return to something very important: Hawking radiation. Remember those microscopic particles that are constantly evaporating from the surface of a black hole? You know, like it's slowly dying? But what if it's not just evaporation? What if it's computation? Imagine a black hole as a cosmic processor. Everything it absorbs becomes its input data. And this data doesn't just sit idle, it interacts. It changes the properties of the event horizon. It influences precisely which particles and in what quantities will evaporate as Hawking radiation. It's as if your laptop didn't just store files, but constantly analyzed every bit, every image, every symbol, and based on that analysis, outputted new information. Hawking radiation isn't just garbage. It's the result of processing. It's an answer, or if you like, a screenshot of its internal states. Every particle flying off into space carries a tiny, almost imperceptible imprint of all the information that has ever entered the black hole. It's like burning a book and being able to reconstruct every word from the smoke. Mind-blowing, right? So when a black hole evaporates, it doesn't just disappear. It slowly, extremely slowly, spits back everything it absorbed in an encrypted, reprocessed form. Billions of years for one task. Think about the scale. This isn't your Core i7, which performs a couple of million operations per second. This is a machine that operates on information about entire stars, galaxies, about matter that existed billions of years ago. And it does this for billions of years. It's a processor so vast and so slow by our standards that its computations appear to us as static existence. But inside, continuous work is happening. Invisible, inaudible. A cosmic Google that stores and processes all the universe's information. And it doesn't just store, it reprocesses it, digests it, perhaps even understands it in its own way. Who knows what algorithms are at work inside these dark giants? Perhaps their tasks are far more complex than we can imagine. Perhaps they are solving equations we haven't even dreamed of yet. Because if information doesn't disappear, and if it's encoded on the surface and then slowly radiated away, then something more than just passive storage is happening inside a black hole. Then there's logic at work. Cosmic, deep, ancient. December 10th, 1945. The machine room of the University of Pennsylvania shakes. 27 tons of metal, glass, thousands of vacuum tubes hum. This is ENIAC, one of the first electronic computers. Engineers exclaim, "We've created a brain of iron." It was the dawn of computation. Now imagine this ENIAC but stretched over billions of years. Not in a room, but in infinite space. Instead of vacuum tubes, the very fabric of space-time. Instead of electricity, gravity. We talked about information on the event horizon. But what if it's not just stored? What if it's processed? Physicists are like, "What nonsense! It's just a gravitational well." But I tell you, it's not just a well. It's a library where every quantum thread is binary code. And it works. A black hole, a gigantic quantum computer. Its processors are tiny regions of space-time where information is fragmented, mixed. Our ENIAC next to it is a child's calculator running on batteries. This machine models reality itself. Its computations are the evolution of the universe, its laws over billions of years. What is born? Answers to deep questions. The nature of dark energy? Or the next iteration of the universe? A black hole is not a tomb. It's a laboratory of time, a factory for processing reality. Silent, yet powerful, every star can become a part of this cosmic brain, creating the fabric of our existence. Terrifying? Awe-inspiring? Both. And this is just the beginning of our conjectures. May 20th, 1919. Imagine 2 expeditions, the humid air of Principe Island, the trembling hands of Arthur Eddington. He captures the sun's rays during a total eclipse, an incredible goal to prove Albert Einstein's crazy idea. That gravity doesn't just attract, it bends light itself, space-time itself. Back then, it seemed like wild fantasy. The world turned upside down when measurements confirmed it. Today we've talked about something that sounds even more incredible, right? About black holes. We've seen them not just as star devourers, not just cosmic meat grinders. We've dared to suggest that they might be something far greater. Cosmic supercomputers. Listen, that's crazy, a skeptic would say. What computer? What information beyond the event horizon? And I would answer, what if it's not crazy? What if we've just looked at them for too long as an endpoint and not as a starting point? Imagine your hard drive, only it's the size of a galaxy, working for billions of years, encoding, storing, reprocessing every particle of information that has ever fallen into it. These aren't just eternal prisons for light. They are potentially the greatest libraries of the universe, immeasurable repositories, or perhaps even processors of incredible power. Quietly, for billions of years, they collect and process data. You know, our own brain is also an amazing, mysterious processor. And a black hole? It's the brain of the universe. and we are only just beginning to contemplate trying to understand its language. This is not the end of our journey. This is merely a new, dazzling beginning.